I'm going to talk about how I've used parallel computations for calculating this object called stochastic expansions that we're using to and for studying SDE's stochastic differential equations. First, I need to introduce what these objects are and what the problem with them is. So just bear with me for a few slides. It's going to be a bit mathematical, but it should be okay. So that's just the abstract. So what is a stochastic expansion? I suppose you're familiar with differential equations, where you have things like this. With stochastic differential equation, we add extra bits like this, where to model noise typically. So WT is typically some kind of random process. You can think of it as Brownian motion, all sort of things. Actually, the theory that we're using, called rough math, allows us to use much rougher random processes than just Brownian motions. And I'll give an example with fractional Brownian motion, for example. But you can imagine using things like delay equations or point processes, all sort of stuff. So the main thing is that the expansion, you can think of it as a bit like a Taylor expansion. That's a local approximation of the solution. And it's written like this. So you start off with X node, obviously. We estimate we are approximating the solution around X node. And then you have some coefficient C times the integral from 0 to t of the first driver, dt in this case, and then some other coefficients plus the integral of with respect to the second driver. And then you start mixing the driver. You first integrate with the first driver, then second, then first, second, and then second, the first, and so on and so forth. And you carry on like that using all the possible combinations. And you can see very readily that this thing is going to explode very quickly. So that's one of the problems using these things. I think that's it. Yeah. So what we want to do is to be able to generate these expansions automatically with Mathematica. Thanks to the symbolic computation that Mathematica can handle, we can do that fairly easily. So this is an example of fractional Brownian motion for, I don't know if you're familiar with this. This is standard stuff in SDEs called Arlstein-Uhlenbeck process, where you have something going to a mean B at a rate A, and you have some noise in the way. And we can show very quickly that with Mathematica that the expansion for these things will be written like this. Okay. And then once we have that, we can just play with this and see what the solution looks like for different parameters around X node. So that gives us a sort of closed formula for the expansion of the solution. Well, so how do we write these things? So as I said, you have to think about all the possible combinations of this of the drivers. So if you have any number of drivers, you're going to use these objects J as superscript alpha, where alpha is a word where each letter gives you the driver you're going to use. So you start integrating with the driver alpha 1, then you integrate with respect to the driver alpha 2, and so on and so forth. So by construction, if you integrate one of these J alpha with respect to another driver K, it's just the same thing as J, the word alpha, and then you put K at the end. But these objects are a very useful property. They are following these things called shuffle product. So if you have two words, alpha and beta, and you multiply the two iterated integrals together like this, the result is the shuffle product of the two words, which is you think about all the possible combinations using the letters in alpha and beta, and you only keep the ones that are in the same order as they were in alpha and beta. So this is an example here. So obviously Mathematica can handle that very easily. You just need to express what times is for these particular objects, and then you can manipulate them as you would for anything. So in this case, you see I got all the possible combinations, but I never have the combinations where 3 is before, is after 4, for example, I think. Okay, but you see that the problem with this is that as soon as you start multiplying these objects together, they explode. Okay, you have a large number of several words. But the interesting thing is that you can think of any power of these things, or any polynomials, can be written as linear combinations of these objects. So you always end up, if you're manipulating polynomials of these things, you always end up with the linear combinations. So that's which you can then do some statistics on fairly easily, like taking the expectation, for example, which is a linear operation. So how to derive these expansions? So imagine you have this SDE. So you have like n plus 1 driver. We typically start, we reserve W0 for time dt. So we write everything in terms of W's. And you just follow this very simple procedure. You start with x node, and then the next approximation would be just the integral, the x node plus the integral of the first function here of your solution with respect to the driver 0, and so on and so forth. Okay? And you just carry on doing that. And again, if we stay in the case where all the f's here are polynomials, so we're going to end up with just linear combinations every time that we can integrate very easily with respect to the things. So for example here, if I have a very simple system here, I start with x naught, and then I integrate with respect to ax and to b, with respect to w naught and to w1, so I get this. So that's, after the first iteration, that's my solution, that's the expansion. And then if I plug that in the formula again here, so I just end up with a linear combination of j's again. So that's what we want to end up with. So in Mathematica, it's fairly easy to do that with just one line of code. And you see if I try here, there you go. So I have a linear combination of j's, and that's the how to write the expansion of this particular system. Okay. Now the problem is, so it looks like everything's done. Okay, we have a program that calculates the expansion for us, that does all the algebra for us, so we have nothing to worry about. The problem is that, again, these objects are getting bigger very, very fast. This is just a graph of the maximum number of terms that you would have to manipulate given the number of iteration and the polynomials you use in your system. So if I start with 2 drivers and just linear functions, you see that this is the log 10 of the maximum number of words. So we already had, well, not that much here. That's 1.4. But if I take just quadratic functions, you see that after 4 iteration, we already to 10 to the power almost 5. Okay, so that would be a lot of things to manipulate. So the solution we have is to reparameterize the system so that the computation is going to be done. It's going to be done in parallel. So it's going to be, we'll be able to do that completely distribute it over a cluster, for example. And we won't ever have to manipulate this massive object. So I think I'll go a bit fast with this slide because that's a bit complicated. It's all in the paper if you're interested. But basically, we introduced this new operation, circle dot, which is defined this way. So we have two words, alpha and beta, and if you want to calculate the circle dot product of these two objects, they're just defined this way. So it's the integral of the first one with respect to the second one, which is equal to this bit. And this bit, obviously, is a shuffle product as before. But the good thing with this is that we can rewrite the Picard iteration this way. Okay. And by doing it this way, so again, R is the number of iterations you're using. By doing it this way, we don't. Let me go to the next slide where everything's explained. So I'm just following the new Picard iteration with the new product, and you see that after 3 iterations, I got a very compact number of, very compact expression, and which you can handle, and you can store somewhere. And this abstract representation have quite a few advantages over the normal one. But it doesn't depend on the particular parameterization of the polynomials fi. All we need to know really is what's the maximum degree of the polynomials, and which appear here. There you go, the 2 here, if we use quadratic functions. And crucially, it doesn't depend on the number of drivers. The number of drivers is actually stuck somewhere deep into the definition of Q. The Q's are defined this way, where you have the number of drivers. So, and it doesn't ever require the explicit computation of the shuffle product. So we can carry on computing Picard iteration of this kind quite far without having to worry about memory or and computing power. And obviously the 2 representations are equivalent. You can go from one to the other. And what we want to do is to go from the Q's, from this representation Q's, to the representation in J, which give us all the statistics we need. So to do that, we go through a few different stages. First you start computing the Picard iteration as before, but in Q, so that's very compact, that's a small expression. And then you expand each, so you can think of this as a polynomial using plus, so that's a normal plus, and using this funny product, which is non-associative and non-commutative, so you have to tell that to Mathematica. But in any case, it is distributive, so you can expand your expression into monomials of this kind, stage 2, you see. And because it's just a linear, there's just a sum of these monomials, you can store all these monomials in some file, for example, and process them individually. Okay. And then that's what we do at stage 3. So we replace the Q's by their definition in terms of J's. And then, again, we end up with the polynomials of J's and circle dot. And then we can explode this into simple monomials in terms of J's and circle dots. So it looks a bit convolved, but the whole idea is to manipulate as small as possible objects at every stage. And again, because at every time we have, at all stages, we have a polynomial, the sum of monomials, basically, we can do that in a distributed fashion. So we can process each monomials individually. So by doing it this way, each process only requires a fraction of what a direct approach would need. And yes, and there's a natural parallelization because it's just a sum. This is just an example of how to do this in Mathematica. Basically, what you need to have is to be able to read a file which is going to store your expression at one particular stage in parallel, and then be able to write in another file, the destination file, in parallel as well. And it was not completely obvious how to do that in Mathematica, and I'd like to thank these two people here for helping me figuring this out. This is just an example where I write 2 to the power I in some original file. Okay, here. Okay. And then what I'm going to do is to take the log2 of these things, but in parallel. So what I first do is to get the position of each entry in the file. Okay, that's just a normal file, just a text file that you can open and edit if you want. So each entry has a particular position in the file, and then you have to distribute this over the kernels. Okay, that's just so that all the kernels will know these variables. These are some temporary files that you're going to write into, and this is the core of the thing. Well, so you're going to assign, so you submit, you're going to assign all the cluster to a particular position. Okay, so you have a list of positions, and this list is going to be shared by a cluster. So cluster 1 is going to take 1 and 3 and 5, for example. Cluster 2 is going to take position 2, 4, and etc. It all depends on the number of clusters available, obviously. And then this we just read. So this bit here tells you what the cluster is going to do, and this bit here and there actually submit all these jobs to the kernels, and this one tells Mathematica to wait that for everything to have been assigned before doing any more computation. And then you just close the files, and then you concatenate all the temporary files. It's something I've noticed that's actually needed. You can't. It's quite dangerous to write on the same file in parallel. You always end up with some corrupted things, or things are missing. So the way it's done here and the way it's done in the code is to go through temporary files. So each kernel is going to be assigned a temporary file on which to write. Okay, and then eventually, when everything's done, you put all them together. Okay. So if I try to run this, it works. So this is the content of the final file. So we should have all the numbers from 1 to 20, because we took the log2 of this thing. And you see that they're in different order, really, depending on. So this one, so has been this is the output of the first cluster, or the first kernel, sorry. This one of the second kernel. So that's how it's done. So if we go through all the stages I've mentioned before for this particular example, so we have a linear drift and a quadratic variant. We define the queues here according to the formula that was in the slide. We specify the maximum degree, the number of iterations we want. this is another control we have. If we end up with words that are longer than max word length, then we just discard them. I'm not discarding any here. And try this. So again, stage 1, and I'm deriving the monomials in Q and circle dot, and then I'm putting the model in. So I'm replacing the Q's by the actual values in terms of J's. It's a bit big. Yep. And then I replace the circle dot by its actual definition in terms of shuffle product. And then once I have that, here, if I stop here, I will have my expansion for 3 Picard iteration for this problem. Obviously, I went to 3 Picard iteration here because I wanted to finish, but if I go to 4, that would take a much longer time, and actually at 4 or 5, it would crash on if you don't use this method. So if you use the normal method, the normal Picard iteration, you would get so many objects that Mathematica would crash. So that there's value in doing this convoluted way of things. So another thing is that so you end up with this big expression in sum of j's, okay? But for certain processes like Brownian motions, we know it's very easy to derive the expectations of these iterated integrals. And if we do that, they actually have a very simple form. They're just polynomials in t in time. So if I take the expression here that I got here, that I'm not showing because it has 362 terms and it's fairly big. If I take the expectation of that thing, it would be just the expectation of each of these single j's, which I can compute very easily, and therefore I have a closed form formula for the expectation of this here, and then again I can play with it and see how it behaves, and so on and so forth. Okay. And so just to wrap up, just want to give a summary of what I've been talking about. So we have this object, these stochastic expansions that provide local approximation of the solution of a stochastic or even deterministic differential equations. They can be used for a whole range of things, but the number of terms in these expansions grow very rapidly. And so with this method, we can distribute the computing to a whole cluster, and it leads to natural parallelization. These are the references if you want to go in the math of it. There's also this fractional OU process I've showed is available on Wolfram demonstration. I'll stop here. Thank you very much.